Looked at two properties of lasers, which were intensity and monochromaticity. We proceed to the third property, which is directionality. So let's understand with the help of this image. Now, by directional, what we mean is something that follows a specific direction, something which is not spread out everywhere and in all directions, right? That's what the name obviously suggests. And that's exactly what. So when you have a laser light, when you flash it, you can generally see the thin beam of light. Let's say I'm seated in the first bench in class and I flash a laser on the board. If your settings are conducive enough, you can actually not only see the image, the point on the board, but the actual beam of laser light, a straight line from the laser I'm holding to the board or to wherever I'm flashing it, provided I have a strong enough laser and all that. So that, but if I flash my, let's say, mobile flashlight, or if I turn on the tube light, it will light up the room, but we will not be able to visualize that entire beam of light from the light source to the wall. So that is because lasers are more directional. So this is what I mean. Let's say this is the source, this is the laser. This is the light source. Let's say it spreads out light in all these directions. And let's say you have another source whose light spreading capacity is limited to this much. Then we would say the latter is more directional, right? So quantitatively speaking, if the angle made by the light rays is smaller, we say the light source is more directional, or it follows a more straight line. So that's the idea. So when I say a laser is directional, and if I give you these two pictures, this one is likelier to be a laser. That's it. So again, to develop a quantitative measure or a numeric way to measure this, we were talking about the angle. So let's say again, this is my light source. This is the topmost ray of light it emits. This is the bottommost ray. I take 2 points at distances d1 and d2 from the source. So let's say this distance is d1 and this distance is d2. Of course, we measure the perpendicular distance from the point, from the source to the point, and not the actual length of the ray. So this is d2, d1. At those respective points, I calculate this diameter of the angle, or diameter, or the angle made. I calculate this length, which is basically a measure of the angle it makes, sort of. And then using that, how do we compute directionality? A2 minus A1 upon 2 D2 minus D1, where A1 is the angle made at a distance D1, A2 is the angle made at a distance D2. We generally take the beam radius instead of the diameter, so A2 minus A1 upon 2, because A1 and A2 refer to the diameter of the beam, we take radius, so A2 minus A1 upon 2 with respect to spatial distance D2 minus D1. So the angle of divergence is given by A2 minus A1 by twice of D2 minus D1, where A2 and A1 are the beam diameter taken at distances D2 and D1 from the laser respectively. So the smaller your angle of divergence, the more directional your light source is. And by properties, lasers are highly directional. That's the third property.